Okay, so in the last video we found the particular solution to our particular problem as being the second half of this equation here. And then we found our general solution by adding together our particular solution and our fundamental solution here. So now all that's left to do is to find out what C1 and C2 are. And in order for us to do that, we need to solve an initial value problem. So that's what we're going to do in this video. So the only way we can solve an initial value problem is if we have some initial values given to us. So for example, if we know the position of our system x at t equals 0 is equal to some value, and as well we need more than one to solve two constants. So we're going to use simultaneous equations, but you need two equations to do so. So we need to know, for example, our initial velocity at time 0. And it's quite common to see a system that has an initial value of its position as being 0 and an initial value of its velocity being 0. And when I say velocity, I just mean the first derivative of position, which is its physical description. So with these given initial values, all we need to do now is plug this into this equation. So our general solution, xg of t equals 0, which is equal to 0. And now all we need to do is impose t equals 0 everywhere we see t in this equation. So we have c1 e to the 0, which is just 1, so c1 times 1. So we just have c1 here, plus, and again c2 e to the 0, which is just c2, plus c2, and again e to the 0 is just 1, so 3/5 times 1 is just plus 3/5, and then the cosine of 0 is 1, so minus a fifth times 1 is just minus a fifth, and the sine of 0 is 0. So this would reduce to 0. And then we can combine this plus 3/5 and minus 1/5 to give us plus 2/5. Okay, great, so let's call this equation 1. And like I said earlier, in order for us to calculate two unknown constants, we need two equations. So our second equation is going to come from this second initial value we have here. So first off, we're going to need to find what the first derivative of our general solution is with respect to t. So the first derivative of our general solution, and for these first three terms here we can just use the chain rule. So this would give us minus 3 times c1 e to the minus 3t, so that would be minus 3 c1 e to the minus 3t plus 1 times c2, which is just c2, e to the t, because the derivative of t with respect to t is just 1, plus, this would be 6/5, 6/5 times e to the 2t, and we know that cosine differentiates to minus sine, so this would flip this sign here, so we'd have plus 1/5 times the sine of t, and sine differentiates to cosine, so this sign here would stay the same, so we'd have minus 2/5 times the cosine of t. And now all we need to do is just input our initial value here. So at t equals 0, and as before we just plug in everywhere there's a t, we just plug in a 0. So this would be minus 3c1 times 1, so e to the 0 is 1, so we would have minus 3 c1, and same again, we'd have plus C2 plus 6/5 times 1, and since the sign of 0 is 0, we lose this term here, and the cosine of 0 is 1, so we would retain this minus 2/5 here. So we'd have minus 2/5, and once again we can combine these terms here, and this is also equal to 0, equals 0. So let's call this equation 2. Okay, so now we have a system with two simultaneous equations that we need to solve. And you probably know already from your algebra classes that this can be done quite easily. You may notice we have a 1c2 in both equations, so we could just subtract this one from this one. However, I think I'll just calculate what c2 is from this equation and then input it into number 2. So c2 from equation 1 is equal to minus c1 minus c1 minus 2/5. So then if we take our value for c2 and put it into here, equation 2 becomes minus 3 c1 minus another c1, and minus 2/5 plus 4/5 is plus 2/5, so plus 2/5 is still equal to 0. So therefore 4 lots of c1s would be equal to 2/5, so c1 is equal to 2/5 times 1/4, which is equal to 1/10. And since we used equation 2 to calculate c1, we're going to have to use equation 1 to calculate c2. So 1/10 plus c2, this is just equation 1, plus 2/5 is equal to 0, so therefore c2 is equal to minus 1/2. So now that we finally have our c1 and our c2 values, we can go ahead and write down our final solution. So after 3 videos, we have our final solution. So to summarize, the first thing that we did in order to solve this was we found our fundamental solution by using our lambda function, treating our function as though it was homogeneous. And we did this in the first video of this mini-series, which was Cal 05.2. The second thing we did was we found our particular solution, which is also known as our non-homogeneous solution, and we did that in video calculus playlist 05.3. Then when we had these two solutions, we found our general solution, which is just both of these added together. And then finally we solved an initial value problem in order to give us the constants c1 and c2 that we got from our fundamental solution, which was in this video. And these 4 steps will work for any second order ordinary differential equation as well. So hopefully this video helps, and I'll leave a link in the description of the other 2 videos in case you want to take another look at those. And as always, if you have any questions or comments, please feel free to pop them in the comments box below. In the next video we're going to take a look at the case where lambda 1 is equal to lambda 2, so we just have a repeated real root. I'll see you there.